The Cauchy distribution, named after Augustin Cauchy, is a continuous probability distribution. It is also known, especially among physicists, as the Lorentz distribution, Cauchy-Lorentz distribution, Lorentz, Ian, function, or Breit-Wigner distribution. The simplest Cauchy distribution is called the standard Cauchy distribution. It is the distribution of a random variable that is the ratio of two independent standard normal variables and has the probability density function. Its cumulative distribution function has the shape of an arctangent function arctan, x. The Cauchy distribution is often used in statistics as the canonical example of a pathological distribution since both its mean and its variance are undefined. The Cauchy distribution does not have finite moments of order greater than or equal to 1. Only fractional absolute moments exist. The Cauchy distribution has no moment-generating function. Its importance in physics is the result of it being the solution to the differential equation describing forced resonance. In mathematics, it is closely related to the Poisson kernel, which is the fundamental solution for the Laplace equation in the upper half-plane. In spectroscopy, it is the description of the shape of spectral lines which are subject to homogeneous broadening in which all atoms interact in the same way with the frequency range contained in the line shape. Many mechanisms cause homogeneous broadening, most notably collision broadening, and Chandler-order radiation. In its standard form, it is the maximum entropy probability distribution for a random variate X for which characterization, probability density function, the Cauchy distribution has the probability density function, where XO is the location parameter, specifying the location of the peak of the distribution, and I cubed is the scale parameter which specifies the half-width at half maximum, alternatively to I cubed is full width at half maximum. I cubed is also equal to half the interquartile range and is sometimes called the probable error. Augustin Louis Cauchy exploited such a density function in 1827 with an infinitesimal scale parameter, defining what would now be called a Dirac delta function. The amplitude of the above Lorentzian function is given by the special case when XO equals 0 and I cubed equals 1 is called the standard Cauchy distribution with the probability density function. In physics, a three-parameter Lorentzian function is often used, where I is the height of the peak. Cumulative distribution function, the cumulative distribution function is, and the quantile function of the Cauchy distribution is. It follows that the first and third quartiles are, and hence the interquartile range is do I cubed. The derivative of the quantile function, the quantile density function, for the Cauchy distribution is. The differential entropy of a distribution can be defined in terms of its quantile density. Specifically, properties, the Cauchy distribution is an example of a distribution which has no mean, variance or higher moments defined. Its mode and median are well defined and are both equal to XO. When U and V are two independent normally distributed random variables with expected value 0 and variance 1, then the ratio UV has the standard Cauchy distribution. If X1, Xn are independent and identically distributed random variables, each with a standard Cauchy distribution, then the sample mean n has the same standard Cauchy distribution. To see that this is true, compute the characteristic function of the sample mean. Where is the sample mean? This example serves to show that the hypothesis of finite variance in the central limit theorem cannot be dropped. It is also an example of a more generalized version of the central limit theorem that is characteristic of all stable distributions, of which the Cauchy distribution is a special case. The Cauchy distribution is an infinitely divisible probability distribution. It is also a strictly stable distribution. The standard Cauchy distribution coincides with the student's t-distribution with one degree of freedom. Like all stable distributions, the location scale family to which the Cauchy distribution belongs is closed under linear transformations with real coefficients. In addition, the Cauchy distribution is the only univariate distribution which is closed under linear fractional transformations with real coefficients. In this connection, see also Mikula's parametrization of the Cauchy distributions. Characteristic function, Let X denote a Cauchy distributed random variable. The characteristic function of the Cauchy distribution is given by, which is just the Fourier transform of the probability density. The original probability density may be expressed in terms of the characteristic function, essentially by using the inverse Fourier transform. Observe that the characteristic function is not differentiable at the origin. This corresponds to the fact that the Cauchy distribution does not have an expected value. Explanation of undefined moments, mean. If a probability distribution has a density function f, x, then the mean is. The question is now whether this is the same thing as for an arbitrary real number a. If at most one of the two terms in is infinite, then is the same as. But in the case of the Cauchy distribution, both the positive and negative terms of are infinite. Hence is undefined. Although we may take to mean, and this is its Cauchy principal value, which is 0, we could also take to mean, for example, which is not 0, as can be seen easily by computing the integral. Various results in probability theory about expected values, such as the strong law of large numbers, will not work in such cases. Higher moments, the Cauchy distribution does not have finite moments of any order. Some of the higher raw moments do exist and have a value of infinity, for example the raw second moment. By rearranging the formula, one can see that the second moment is essentially the infinite integral of a constant. Higher even-powered raw moments will also evaluate to infinity. Odd-powered raw moments, however, do not exist at all, which is distinctly different from existing with the value of infinity. The odd-powered raw moments are undefined because their values are essentially equivalent to since the two halves of the integral both diverge and have opposite signs. The first raw moment is the mean, which, being odd, does not exist. This in turn means that all of the central moments and standardized moments do not exist, since they are all based on the mean. The variance a euro, which is the second central moment a euro, is likewise non-existent. The results for higher moments follow from Haar paragraph LDER's inequality, which implies that higher moments diverge if lower ones do. Estimation of parameters. Because the parameters of the Cauchy distribution don't correspond to a mean and variance, attempting to estimate the parameters of the Cauchy distribution by using a sample mean and a sample variance will not succeed. For example, if n samples are taken from a Cauchy distribution, one may calculate the sample mean as. Although the sample values xi will be concentrated about the central value xo, the sample mean will become increasingly variable as more samples are taken, because of the increased likelihood of encountering sample points with a large absolute value. In fact, the distribution of the sample mean will be equal to the distribution of the samples themselves. That is, the sample mean of a large sample is no better an estimator of xo than any single observation from the sample. Similarly, calculating the sample variance will result in values that grow larger as more samples are taken. Therefore, more robust means of estimating the central value xo and the scaling parameter I³ are needed. One simple method is to take the median value of the sample as an estimator of xo and half the sample interquartile range as an estimator of I³. Other, more precise and robust methods have been developed. For example, the truncated mean of the middle 24% of the sample order statistics produces an estimate for xo that is more efficient than using either the sample median or the full sample mean. However, because of the fat tails of the Cauchy distribution, the efficiency of the estimator decreases if more than 24% of the sample is used. Maximum likelihood can also be used to estimate the parameters xo and I³. However, this tends to be complicated by the fact that this requires finding the roots of a high-degree polynomial, and there can be multiple roots that represent local maxima. Also, while the maximum likelihood estimator is asymptotically efficient, it is relatively inefficient for small samples. The log likelihood function for the Cauchy distribution for sample size n is. Maximizing the log likelihood function with respect to xo and I³ produces the following system of equations. Note that is a monotone function in I³ and that the solution I³ must satisfy. Solving just for xo requires solving a polynomial of degree 2 ⁡ 1, and solving just for I³ requires solving a polynomial of degree n. Therefore, whether solving for one parameter or for both parameters simultaneously, a numerical solution on a computer is typically required. The benefit of maximum likelihood estimation is asymptotic efficiency. Estimating XO using the sample median is only about 81% as asymptotically efficient as estimating XO by maximum likelihood. The truncated sample mean using the middle 24% order statistics is about 88% as asymptotically efficient an estimator of XO as the maximum likelihood estimate. When Newton's method is used to find the solution for the maximum likelihood estimate, the middle 24% order statistics can be used as an initial solution for XO. Circular Cauchy distribution: if X is Cauchy distributed with median I1/4 and scale parameter I³, then the complex variable has unit modulus and is distributed on the unit circle with density. With respect to the angular variable I equals arg, z, where and I expresses the two parameters of the associated linear Cauchy distribution for X as a complex number. The distribution is called the circular Cauchy distribution, also the complex Cauchy distribution, with parameter I paragraph. The circular Cauchy distribution is related to the wrapped Cauchy distribution. If as a wrapped Cauchy distribution with the parameter I equals I1/4 plus I³ representing the parameters of the corresponding unwrapped Cauchy distribution in the variable y where I equals y mod 2 I euro, then see also McCullough's parametrization of the Cauchy distributions and Poisson kernel for related concepts. The circular Cauchy distribution expressed in complex form has finite moments of all orders. For integer RA per mil 1 yen. For I1, the transformation is holomorphic on the unit disk, and the transformed variable u, z, I, is distributed as complex Cauchy with parameter u, I paragraph, I. Given a sample Z1, Zn of size n greater than 2, the maximum likelihood equation can be solved by a simple fixed-point iteration. Starting with I paragraph, 0, equals 0. The sequence of likelihood values is non-decreasing, and the solution is unique for samples containing at least 3 distinct values. The maximum likelihood estimate for the median and scale parameter of a real Cauchy sample is obtained by the inverse transformation. For Na per mil for currency, closed-form expressions and N4. The density of the maximum likelihood estimator at T in the unit disk is necessarily of the form where formulae for P3 and P4 are available. Multivariate Cauchy distribution: a random vector x equals a euro squared is said to have the multivariate Cauchy distribution if every linear combination of its components y equals a1x1 plus akxk is a Cauchy distribution. That is, for any constant vector ark, the random variable y equals or euro squared x should have a univariate Cauchy distribution. The characteristic function of a multivariate Cauchy distribution is given by where xo, t, and I³, t, are real functions with xo, t, a homogeneous function of degree 1 and I³, t, a positive homogeneous function of degree 1. More formally, for all t, an example of a bivariate Cauchy distribution can be given by. Note that in this example, even though there is no analog to a covariance matrix, X and Y are not statistically independent. Analogously to the univariate density, the multidimensional Cauchy density also relates to the multivariate student distribution. They are equivalent when the degrees of freedom parameter is equal to 1. The density of a k-dimension student distribution with 1 degree of freedom becomes. Properties and details for this density can be obtained by taking it as a particular case of the multivariate student density. Transformation properties: if then, if and are independent, then, if then, McCullough's parametrization of the Cauchy distributions, expressing a Cauchy distribution in terms of one complex parameter, define x Cauchy, I, to mean x Cauchy. If x Cauchy, I, then, Cauchy, where a, b, c and d are real numbers. Using the same convention as above, if x Cauchy, I, then, Cauchy, where Cauchy is the circular Cauchy distribution. Related distributions, students' t-distribution, non-standardized students' t-distribution, if independent, then, if x log Cauchy, 0, 1, then ln, x, Cauchy, 0, 1, the Cauchy distribution is a limiting case of a Pearson distribution of type 4, the Cauchy distribution is a special case of a Pearson distribution of type 7. The Cauchy distribution is a stable distribution, if x stable, 1, 0, I cubed, I 1/4, then x Cauchy, I 1/4, I cubed. The Cauchy distribution is a singular limit of a hyperbolic distribution, the wrapped Cauchy distribution, taking values on a circle, is derived from the Cauchy distribution by wrapping it around the circle. Relativistic Breit-Wigner distribution. In nuclear and particle physics, the energy profile of a resonance is described by the relativistic Breit-Wigner distribution, while the Cauchy distribution is the Breit-Wigner distribution. See also, La copyright v flight and La copyright v process, Cauchy process, /distribution, references. External links, Haswinkel, Michiel, ed., Cauchy distribution, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Earliest uses, the entry on Cauchy distribution has some historical information. Weierstein, Eric W., Cauchy distribution, MathWorld. GNU Scientific Library Euro Reference Manual.